Good afternoon. During the last lecture, I introduced the notion of reparameterization of a curve and the definition of a closed curve. The first goal of today is to see how to modify the notion of reparameterization in order to apply it to a closed curve. There are two reasons why we should modify the definition of reparameterization for a closed curve. So two reasons. The first one is the fact that we want that the reparameterization of a closed curve to be a closed curve. Now let's look at the definition of closed curve, and you see that gamma must satisfy this list of conditions, that is the value of gamma and of its derivatives at the endpoints of the interval of definition must coincide. Now let's look at this formula. This formula gives you the expression of the first derivative of the reparameterization of gamma, and as you can see, it involves the first derivative of the smooth bijection phi, which is used in the definition of reparameterization. So this forces us to impose a condition on phi. So I will write that since the reparameterization of a closed curve must be a closed curve, then we need to require that the derivatives of phi match at the endpoints of its domain. And the reason why here I mention all the derivatives of phi is that we want not only that the first derivative of gamma to match the boundary point of the interval of definition, but also the higher order derivative of gamma must coincide at the boundary points. So you can iterate this computation, and if you try to compute gamma tilde second, gamma tilde third, and so on, you will get, by the chain rule, a formula involving the higher order derivatives of phi. So this is why all the derivative of phi must match at the endpoints of its domain of definition. The second condition is that a reparameterization can have different point can have a different point at which it begins and ends. Now, the simplest way to allow a reparameterization to have a different beginning and ending point is the following. We proved last time the proposition 1.27, which ensures the existence of a periodic extension of a curve gamma, gamma hat from R with values in Rn, and we are going to use it in the following way. Consider for lambda in R the restriction gamma lambda of gamma hat to the interval a plus lambda b plus lambda. Gamma lambda is of course a closed curve because it's the restriction of a periodic curve gamma hat of period b minus a, and it has the same trace as gamma, but with different endpoints. With different beginning and ending point, which is given by gamma lambda a plus lambda, gamma hat gamma a plus lambda equal to gamma hat b plus lambda. So we are now ready for giving the definition of reparametrization for a closed curve. So the definition. (1.28). So let gamma define on AB with values in Rn a closed curve a reparametrization of gamma is a function gamma, of the form gamma tilde given by gamma lambda composed with pi defined on the interval CD with values in Rn where lambda is a real number and phi is a bijection, is a smooth bijection which sends the interval CD onto A plus lambda B plus lambda. With, of course, nowhere vanishing derivative. This condition is required in order to get a regular curve whose derivatives all match at C and D. Using this definition of reparametrization for a closed curve, you can prove this interesting result, of which we will not see the proof. It says that two simple closed curve have the same trace if and only if each is a reparametrization of the other. The next goal of the class of today is the introduction of the notion of curvature. So suppose that gamma from I to Rn is a regular curve. What we want to do is the following. So we want to introduce a function called curvature function, or simply curvature, k defined on I with values in 0 plus infinity, such that k of t for any t in I measures how sharply the trace of gamma bends as it passes the position gamma t. We want also that the function k is independent of the reparametrization, the parametrization. Why? This is easy to understand. If gamma tilde is a reparametrization of gamma, and k tilde is the curvature of gamma tilde, then we want that the two parameterization to assign the same curvature to each point of the trace In other terms, we must have k tilde to be equal to k composed with phi. Why? Suppose that phi is the map sending I tilde into I. So I want to recall that I is the domain of definition of gamma, and gamma tilde is the domain of definition, sorry, I tilde is the domain of definition of gamma tilde. So if gamma tilde is this reparametrization of gamma, then we have that if D is phi of C, so if C is this point and D is this point, then we have by definition that gamma tilde of C is given by gamma of phi of C, and this is equal to gamma of D. And this formula says that the maps gamma and gamma tilde send respectively the points D and C to the same point on the trace. Consequently, we want K of C to be equal to K of D. K is a curvature function of gamma, and K tilde is the curvature function of gamma tilde. And this is possible if K tilde is related to K by K tilde equal K composed with pi. And if this is true, then you have K of phi of C, but phi of C is this, so this is true. Okay, so let's try to construct a function which has all the properties I listed. Okay, so let's start from the notation I will use. So the velocity vector of gamma is gamma prime t, and the acceleration vector or acceleration function is given by gamma second t. You are able to compute v tilde, velocity vector or velocity function of gamma tilde, and this is given by this formula, which can be easily obtained by chain rule. Phi prime of t times v of phi of t. Why? Because this is gamma tilde prime t, that is gamma composed with phi prime evaluated at t. You can also compute the acceleration vector of gamma tilde, that is A tilde equal gamma tilde t, and this is nothing but then V tilde prime t, but V tilde t is here. So once again, by chain rule and by the rule of the derivative of a product of two function, precisely a scalar function and a vector function, you get that A tilde t, this is the derivative of the scalar function times this function, plus the scalar function multiplied by the derivative of this function here, that is phi prime of t, times the derivative of this by chain rule is phi prime times v prime, but v prime is a, the acceleration of gamma. So I have phi prime t squared times the acceleration of gamma evaluated at phi of t. And the next step is to consider the orthogonal let's say consider the part, no, let's say consider the orthogonal part of this vector precisely we will consider the component of this vector which is orthogonal to the velocity, that is the component A tilde orthogonal to the velocity vector of gamma. Okay, let's observe this formula. We have there is a component which is parallel to the velocity vector of gamma, and another one involving A, which can have a component which is parallel to V and a component which will be denoted by A orthogonal, which is orthogonal to V. So A tilde orthogonal T, it is given by 0 because as I told you, this component is parallel to V plus the orthogonal part of this one, which is phi prime T square A orthogonal of phi of T. Some of you could ask me why I am taking the orthogonal part of A tilde. The reason is that in the past we already tried to decompose the acceleration vector of a curve, and we wrote this formula: A parallel to T plus A orthogonal to T, where this is parallel to V and this is orthogonal to V. Later, we also proved the geometric meaning of the length of this vector. We proved that the rate of change of the speed, which is the length of this vector, is equal to the component of A of T in the direction of V of T. So this means that we gave a meaning to this vector here. What about this one? Intuitively, if A parallel encodes the change of rate, the rate of change of this length here, then this one will encode the change of direction of the vector V. And intuitively, this vector here will be responsible, will be related in some way to the curvature and to the change of direction of the curve. Okay, so in summary, we proved that V tilde is phi prime V. This is a formula which I unfortunately erased. And this formula here says that A tilde orthogonal is equal to phi prime square times A orthogonal. I dropped the dependence on T for more clarity. A first idea for defining the curvature function could be to try with k equal to the length of a orthogonal. This is what follow, at least intuitively, from the previous discussion. But this is not the good formula. Why? It's written here. If I define k as the length of a orthogonal, what happens to k tilde? The curvature of the reparameterization of gamma? Simple. It is the length of this vector here. And because of the presence of this function, the result is that k tilde would depend on the reparameterization, and we don't want it. The good definition of k is instead the following. So let's write not good or not correct. The good idea or the right idea is to try with this definition. K equal length of A orthogonal divided by the length of V squared. Why? Because if we divide, if we look at k tilde, the curvature function of gamma tilde, this will be given by A tilde orthogonal divided by V tilde square, and this is phi prime square length of A tilde, A orthogonal divided by phi prime square length of V square. And as you see, this function disappears by cancellation. So the good definition is the following one. Definition 1.30. Let gamma define on I with values in R be a regular curve. Its curvature function k from I with values in 0 plus infinity is defined as maybe I don't need this formula anymore. K of t equal the length of A orthogonal t divided by the length of V t square. The reason why we impose a gamma to be a regular curve is that we need to be sure that the denominator is always non-zero. As already told you before, this is a good definition, and the computation we made here implies that k tilde is given by k composed with phi. This is true because here I am using a simplified notation. I drop the dependence on t, so when you use this formula, remember that this means a orthogonal of phi of t, and this means v of phi of t. Okay. If we solve this equation for the length of A orthogonal of T, then we get that A orthogonal T is a length given by K of T times the length of Vt squared. So finally, we are able to provide an interpretation for the orthogonal component of the acceleration. This formula says that its length is given by the product of the curvature function times the square of the length of the vector function. So the orthogonal component of the acceleration is bigger if the curvature is larger and the point moves along the curve with larger speed. Now let's consider a special case. That is, let's consider curves which are parameterized by arc length. So gamma is parameterized by arc length, or equivalently has a unit speed. That is, this vector is length 1. We have a proposition 1.31 which says that k of t is just the length of A of t that is the length of gamma second t. Let's prove it. Okay, the formula for the curvature, the definition for the curvature is on the blackboard. So the denominator, according to this hypothesis, is equal to 1, it remains to prove that the numerator coincides with the length of AT. Why is this true? By hypothesis, the length of the vector v of t, that is the length of gamma prime of t, is equal to 1. That is gamma prime t multiplied by itself is 1, that is a constant. This implies, by proposition 1.18 part A, I said something wrong. Just by proposition 1.18, we have that gamma prime of t is orthogonal to gamma second t, that is v of t is orthogonal to a of t. This implies that if we consider this decomposition, the component which is parallel to v is 0. This is 0, and a of t coincide with a orthogonal of t. And this is the end of the proof, because we proved that k of t, given by definition by this formula, coincide with the length of a of t. And this is, by definition, gamma second of t. If you don't want to use a proposition 1.18, you can prove that gamma prime is orthogonal to gamma second just by differentiation of gamma prime t equal to 1. And you will get immediately the same result. Okay, let's see one example. Let's prove that a circle of radius r has a constant curvature k equal to 1 over the radius. A parameterization of a circle or radius r is gamma t equal r cosinus of t, r sinus of t, with t in 0 to pi. In order to compute the curvature, we need to compute the velocity vector and the acceleration vector of this curve. So v of t is minus r sinus of t, r cosinus of t, and the acceleration vector is given by minus r cosinus of t minus r sinus of t. Observe that the vector a of t is orthogonal to the vector v of t, because the inner product of these two vectors is 0. So once again, exactly as in the case of curves parameterized by Hack-Length, we have that a of t coincides with a orthogonal of t. And of course their length as well. Now it remains to use the definition of curvature. So k of t is the quotient of a orthogonal t divided by the length of v of t squared. But the length of this vector is given by r, and the square of the length of this vector is given by r squared. The result is 1 over r. The next step is the introduction of a spatial orthonormal basis of vectors that will be very useful in the civil. So definition 1.33 says that if gamma is a regular curve, we can define the unit tangent vector as t of t equal to the quotient of the velocity vector and its length with t in I. And it's something here. The unit normal vector as n of t equal a orthogonal of t, the orthogonal component of the acceleration, divided by its length. A remark is necessary because when defining this vector we are dividing by the length of the orthogonal part of the acceleration, so a orthogonal t must be a vector of non-zero length, that is k of t must be non-zero. Otherwise, this is not defined. It is clear that the collection of vectors Tn is orthonormal. So let's write is an orthonormal basis of their span. Why this collection of vectors is orthonormal? By definition, they are vectors of length 1, because for defining t and n, we consider a vector and we divide it by its length, and clearly they are orthogonal. Why? Because the tangent vector, the unit tangent vector, is parallel to the velocity vector, and the unit normal vector is parallel to the orthogonal component of the acceleration vector, which is orthogonal to the velocity vector. So this vector is orthogonal to this one. This definition allows us to find another formula for the curvature function. So another formula for the curvature function. This is the content of proposition 1.34. If gamma defined on I with values in Rn is a regular curve, then k of t, the curvature function, is the length of t prime t over the length of the velocity vector for all t in I. Okay, let's prove this formula. Okay, let's observe that the vector A, the acceleration vector, by definition is given by gamma second. That is, A is V prime, because V is gamma prime. By definition of unit tangent vector, I can write V as t times its length. So I can write here t v prime Now let's apply the formula which gives us the derivative of the product of a scalar function and a vector function. We get t prime length of v plus t derivative of v prime. Now let's observe that t prime is orthogonal to t. Why? Because t is a vector of length 1. This implies, by differentiation, that t prime t is equal to 0. So what is this? This is the decomposition of the vector A into the sum of two vectors which are orthogonal. If they are orthogonal, then this one, which is parallel to the velocity vector, will be A parallel, and this one, which is orthogonal to this one, will be A orthogonal. So what we found? We found another formula for A orthogonal. So an interesting intermediate result is that A orthogonal is t prime times v, length of v. Now it remains to prove our formula for k of t. So k of t, by definition, is the length of A orthogonal divided by the square of the length of v. Now I replace the first formula into the second one, and I get length of t prime times v. I take its length and I divide by the length of v square. So I get length of t prime divided by the length of v. And this is the proof of this formula. Okay. The next result I want to present is an alternative expression for n. By definition, we have that n is a orthogonal divided by its length, but a few minutes ago we found another formula for a orthogonal. So we have t prime over times the length of v divided by the length of t prime times the length of v. And this reduces to t prime over length of t prime. Now let's use a proposition uh, 1.34 again. That is this formula here. Let's drop the dependence on t. We get that the length of t prime is k times the length of v. Then if you look at this formula, this implies that t prime is n times the length of t prime, but we have a formula for the length of t prime, so we get n times k times the length of v. And so we got the following result: proposition 1.35. If gamma defined on I with values in Rn is a regular curve, then at every time when k is different from 0, we have t prime equal to k length of v times n. I would like to make a remark This formula makes sense only when k is different from 0. This is why we need this hypothesis. Because otherwise, when k is 0, the right hand side would be equal to 0, while the left hand side would not. A consequence of this formula is this inequality t prime multiplied by n is equal to k length of v. This formula is immediate. To obtain, I multiply both sides by n and use the fact that n is a length of n is a vector of length 1, but this is also equal to minus n prime t. How to prove that this is true? Simple. We observe that the inner product of t and n is 0 because t and n are orthogonal. Then by differentiation we get t prime n plus t n prime equal to 0. And you get immediately that t prime n is negative n prime t, which is exactly what I wrote here. Okay, I think I have only a few minutes. During the last minutes of this lecture, I will present one example. What is the curvature of a graph at a critical point? So we already know that if f is a function defined on an interval I with values in R, having a critical point at t0 in I, that is f prime at t0 is 0, then a parameterization of the graph of f is given by gamma t equal to t f of t with t in I, of course. And we want to compute k at t0, not at any point of the graph, but only at the critical point of f. So let's compute the velocity vector. V of t is gamma prime of t. This is 1 f prime of t. A of t is v prime of t. This is 0 f second of t. So we have that vt0 is 1, 0, because t0 is a critical point, and at0 is 0 f second of t0. Observe that this implies at0 is orthogonal to vt0. Why? Because the inner product of these two vectors is 0. So this says that at0, which can be decomposed as a parallel t0 plus a orthogonal t0, this is just a orthogonal t0, because this component is 0. Then the formula for the curvature says that k t0, this is the length of a orthogonal t0, divided by the length of vt0 squared, and this is equal to f second t0 divided by the length of vt0, which is 1. So it is just f second t0 in absolute value. So the conclusion is that the curvature at a critical point is the absolute value of the concavity, that is the second derivative at the critical point. That's all for today. Thank you for your attention.